thanks for coming today. And I'm Jason Harrelson, and I know I've talked to quite a few of you already, quite a bit. But I guess today what I'm going to do is really just talk through the trumpet, the mechanics of how it's designed and built, and then include the mechanics of the human being behind it, because both halves of the equation are what make up trumpet playing or brass playing. And I'll do that by kind of a question and answer type setup where we explore together how the trumpet was designed and how it works, and understand some of the acoustic principles. And maybe some of you know that already, and we can just dive deeper into questions later on. And then, of course, the mechanics of the embouchure. And there are lots of different types of embouchures out there, but the basic mechanics are almost always the same because we all have lips and teeth and a mouthpiece, so there's not too much that's very different. So I guess the first question is, this is something I ask my students when I used to teach beginner students years ago. I would always ask them, well, how does the trumpet work? And that's where we would always start in our first lesson. I'd say, well, how does it work? What happens? Because this is just a bunch of plumbing, but how does it make music? How does it make sound? So I guess that's the first question. Think to yourself, of course, what happens when you play the horn? What mechanisms are in place to create the sound, and why does it sound like that? So, of course, everyone knows we have air, we have lips, we have the instrument. I'm going to leave the air and lips out for now, just talk about the instrument, and then we'll get into embouchure and all that stuff in a few minutes. So, the trumpet, when you play an open note, the air goes through the horn, through the tuning slide. It bypasses the third and the second and the first slides, and it comes back out the bell. Everyone knows that, right? You may not stop and think about it very often, but when somebody first sees the trumpet, they probably just have no idea how that works. So, can anyone tell me why do we have the valves in? What's the point?
Fill in the gaps in the harmonic series.
Sure. So when you play open notes, then you get certain notes. You get C, the pedal C, then you get C below the staff, and G and C and E and G, E flat, C on up. Then the rest is the C scale. So if we want to play the other notes, then you need to make the tubing change. So what happens when I press the second valve down? Sure. So it makes it a little longer, so all the partials are now a half step lower, right, in theory. And then the first one, of course, is 2 half steps, and we have all the combinations, so we can create all of the notes. And then we also have the option of alternate fingerings. So that's pretty basic. We've got a length of tubing that gets longer. You could think of it almost like a trombone, although we came up with a mechanism of not having to move a slide. So really, what happens inside the trumpet? Why, or how or why, can it amplify what you put into it and make it, 100 times louder than your voice? What's happening then? It's kind of mysterious, right?
It's a resonance in the horn.
Sure. So it's a resonating cavity. The volume and the length of the horn is going to resonate at a specific pitch, but it'll only do that if you introduce that specific pitch. And that's why we have different partials that we can play as we play trumpet. The reason you can play so many different notes on the trumpet is because those are the natural overtones of that length of tubing. And it is possible to create those overtones in just a plain tube or like a bell, like in a vibraphone or a marimba. There are ways to, especially in a tube, it's easy to overexcite the air inside it and create the overtone series so you can actually hear it. But it's always there. If you ring a bell or something, the whole natural overtone series of whatever that space is there. Now, we just are exciting the different resonating parts of the overtone series. So, how do we do that? That gets into the embouchure side. But how do we do it? Because we do that, the instrument doesn't really do it. If we're playing a C, we're playing a low C, and then we go up to the G, what really is changing? basically what we're doing is we're exciting the air inside the instrument at a different frequency that still matches the overtone series of the length of the tubing. And believe it or not, I hardly ever think about this stuff except when I talk to people, because we all take it for granted. It's just part of life. As we go higher and higher, then of course they become closer together. So as you go higher on the overtone series, or the partial, and there's a mathematical formula that basically represents what's going to happen, which notes, which partials are going to sound. But the reason that sometimes we don't play a note that really sounds right, or that even speaks at all, a lot of times is because what we put into the horn doesn't match one of those portions. So if you go to play a high C and you accidentally hit a B flat, it's usually because you didn't excite the air at that frequency. You didn't give the right airspeed, maybe, the right frequency. And we'll talk about all that stuff on the embouchure side in a minute. So why does it amplify the sound? Because all I'm doing is this. How does that make it so much bigger? That's a great answer. You know what's funny is for years I've given clinics like to grade schools and sometimes the whole school district, and there are kids who will just like say stuff like that. It's magic, or it kind of is. It feels like it. Especially when you compare it to things that plug in the wall. It's like all the gadgets that we have in the world, and then like acoustic instruments are still so cool. It's pretty amazing. So why does it amplify the sound?
I can say what I think it does. I think you get a pressure wave that propagates to the end, and most of it actually reflects off the end and comes back. And if that goes at the right rate, you end up adding amplitude to the pressure wave at the same spots. And then at the end of the bell, some small percentage of that gets transmitted out the bell and into the room, but most of the energy actually stays in the horn to keep adding on to that amplitude of the pressure wave.
And what you're describing is the standing wave.
Tim, I like what you're saying, but I like magic better.
Yeah. Well, a little bit like if you were to stand with, well, this is quite a great example. If you were to like hook up a rope to the end, on one end, and sit there and do it at just the right rate, you'll see these waves doing this for one mode. If you get it like twice as much, you can get 3 of those in there.
Right.
But it has to be at the right rate, otherwise it won't. It has to be at the rate that the propagation to the end and back is, otherwise you'll screw it up. That'd be sort of like trying to play in between a C and a G, right? Trying to get right smack in the middle. It's not going to really resonate that well.
Right, and I can demonstrate that, and obviously you know the answer because we have an engineer here. I mean, that sounds horrible, right? But what's happening is exactly what you're saying. If everything is in sync, if you are if you're putting in the right airspeed and you're creating the correct frequency because your lip length and everything is just doing it right, then you get what we call resonance, which is really just exactly what you said. Basically, that standing wave inside there is so in sync that it just builds up with more energy on the partials. And whichever partial you're on, it's going to sound. The reason I bring that up is because that part is something I think about a lot. And it's something most people can't even define. You actually did a great job of giving your rendition of what happens there. There's actually, it's not like a pure science that people have for sure figured out, because people are still working on this problem in standing waves, trying to understand how and why they lose energy. Standing wave efficiency is something I talk about all the time. It's certainly nothing I invented. It's something that I just studied in physics and then applied to brass instruments. But I'm lucky enough to come across clients and people around the country who study this stuff, as engineers and scientists for a living, and they've really shed a lot of light on really what happens. But this problem exists in cell phones, in cell phone towers, in almost all communications, in all electronic devices. Standing wave efficiency is very important, and not just efficiency. A lot of times they're not even focused on efficiency unless they're transmitting, like a radio wave or a cell phone tower. But interference, and just making sure that all the frequencies are right, and everything is clean. But what happens here on a trumpet, the reason I think about it is because when you put the right frequency, when you create the right frequency, by putting the right, basically exciting the molecules in the air at the right frequency, by putting the right amount of air in, at the right speed, with the right lip length, when you get it all synchronized and it works, then you can still have problems. So on some horns, I can play these things. And sometimes I will have like a major issue with one of the partials. And I'll be like, well, we need to figure out what's causing that. So does anybody have any idea of why that could happen, or how it happens? Or have you ever experienced that? Have you ever played a G above a staff and been like, man, every time I hit that G, it's either way out of tune, or I can't hit it clean,
Go ahead.
Is that a situation where you somehow, your waveforms are like fighting each other rather than resonating more somehow?
It definitely can be a possibility. And I try to categorize that problem as extra interference that comes into the horn, and I'll explain that in a minute, but yes, that can be one way that happens. Any other ideas? Because that is right, but there's more than one answer.
When I chip a note, I feel like it's because the natural resonant point, the frequency of the resonance, is not coincident with the pitch I'm trying to hit.
Sure, okay.
So like a lot of times I'll have 1 and 2 hit the A, which is always high on most of the horns I play, right? And if I don't pull out, right, I'm always going to miss that, because it wants to resonate in the horn higher
At a different pitch than you want.
at a different pitch that you want, right?
Sure. That can always be a problem. And so basically your reasoning is that you're introducing, you're trying to compensate for something in intonation, and you're introducing maybe a frequency that's not quite matched up.
Yeah.
Of course, that would be it. What I'm really looking for here, nobody ever gives me this answer, because it's what I do, is the only reason I know it. What happens though is, every time that you play a different partial in the overtone series, then you get more nodes and antinodes. Does anybody know what that stuff is? Yeah, so nodes and antinodes, pretty simple. If you were skipping rope, then if you have 2 kids skipping rope here, then the center of it would be the antinode. And the antinode in jumping rope would be at the very center, the very middle highest peak. So if you were skipping rope, you would not want to be in that center section unless you were synchronized with it, because you would hit with it. Because the rope itself has most of its energy that's like there ready to exert itself at the very peak of the rope. As you go down the rope on either side, it has less and less energy that it can exert on you if you were to run into it. Okay, so I focus mostly on the peak of the antinodes, because if I play the fundamental of the horn, then the sound wave is basically reflecting from the back of my mouth, or wherever the closed spot is in my mouth, all the way to a little ways outside of the belt, okay, a few inches out there, just because it reflects on the static air out here, okay? You don't really have to think about that too much. But the antinode, so each end is the node. Inside my mouth is the node, and out here is the node, and the antinode's in the middle. So skipping rope, of course, that analogy, then somewhere in the middle of my horn is where all that energy is being exerted. And that would be on my pedal C. Now if I play C above it, which is this one, now what do I have? So what do my nodes and antinodes look like on the horn?
So twice the fundamentals. Okay. So that was, you have like 2?
Yes, 2. Exactly. So you have 2 waves, or 2, if you were skipping rope, like you were saying a few minutes ago, if you skip it at the right frequency, then you can get 2, right? And that's what we do when we play the next partial. We're just exciting it at the other frequency. when that happens, if you were to use an ultrasound or an interferometer or something like that to see the movement, you could see that there's a lot of energy being exerted where the antinodes are. So eventually, you could map out the trumpet and see all the antinodes where they're exerting pressure. And from that, you could determine where you were losing energy and then why that G doesn't lock in solid. So that's what I did when I was in college. When I was in college, I became obsessed with the idea of building a better horn. And it was because I played a box Strat that was from like '63. And my friend Dave played on a box Strat that was from like '93. It was brand new. And his horn, I didn't know this, he was a really good player. He locked in all his notes. He sounded beautiful all the time. And he was my competition. We were the two performance majors at my school in our class. And man, I would do anything to play as good as Dave because he was just so solid and such a great player. And he started playing and practicing like 10 years before me. So there are good reasons why he wasn't that great. But part of it was the horn because, and I never knew this, I was not a gearhead. I didn't know anything about horns really. But my dad had taught me enough about mechanics and engineering to at least think about those things. And one day Dave said, "Hey Jason, can I try your horn? I heard that these old Bachs from the 50s and 60s are really amazing, and I want to compare it to mine." I said, "Well, sure." You know, this was the beginning of the internet, so we had those like orange and green screens in our school where you could type, and there was this place called T-Pin, and basically you'd log in, and then you type a question, and then you know, someone who you didn't even know who they were would write back, and they'd be like a famous trumpet player. They'd write back and they'd be like, "Oh yeah, well that probably works like this," and you'd type for a while, and then we'd talk about it. We would sit next to each other in the computer lab and type, and then 3 days later we'd find out the guy we were chatting with was like principal of the Philadelphia Orchestra or something. They were like, "Oh, I had no idea," you know, because we didn't know anything, you know. The internet, I mean, unless you knew those people, or you read the ITG journal, like, religiously, you didn't know who these people were, you know. So, anyhow, these orchestral guys, we were orchestral majors, these orchestral guys were saying, "Yeah, you need to play the older Bachs, because they're the better ones." So he says, "Jason, let me try your horn." And he gave me his horn. And I went to the practice room and I played the Intimate Sonata, which was what I was working on at the time. I was like, bum, 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 ba-da-ba-bum. Well, there's that part that goes, da-da-da-da-da-da. You know, it's really difficult to play that. It's like, I don't know, double or triple pianissimo or something, right? And on his horn, I was like, I cannot believe it. Like, I just nailed that the first try. It was amazing. I thought, there's something about this horn that's different than mine. And it's the first time I ever thought that, you know? I'd never in my life thought one trumpet would really play any different than another.
Which was his, the older one or the?
His was a 93 Bach.
93.
Mine was a 63. And my 63 Bach was given to me by my father as a graduation gift. He bought it for $200 and had it refurbished. It had been like dented up and completely abused for years before that. And what we learned later on was, it was my uncle's horn before that. He had it refurbished before, because he said it was trashed when he got it. So it had been refurbished completely at least twice. And the metal on the bell was so thin that we would all mess around bending it, because we thought it was fun. We'd like bend the bell, and then bend it back, and you could put your thumbprint in the bell. It was that thin. And then you could like kind of iron it out with your fingers. Somehow I won an audition on that horn as a freshman to get into the top band, and sat next to Dave, and then after playing his horn, I was like, man, your horn is amazing. I thought to myself, I could play so much better on that horn. I had no idea, you know. I've been working so hard on this horn that just was losing energy. And Dave said, yeah, you can have your Bach back. I don't know about those 60s Bachs. He gets back on T-Pin and tells these orchestral guys, yeah, I don't know about that, you know. They don't play that well. You know, and that's how like weird hearsay comes about on the internet. Somebody will try one thing and then everyone thinks, oh, that's backed, because enough people read that one link, you know. Back then it wasn't permanent. T-Pin was like temporary. It was just chat windows. Nothing would stay online. Today you go online and you can read all kinds of things about how stupid I am, because I would dare try to do something different. But you know, in reality, I mean, how else are you going to learn about anything unless you try new things? So that original Bach that did not play well really inspired me to eventually do what I do today. I didn't expect to go in this direction at all. I thought I'd be a performance major in an orchestra, you know. Maybe it's a good thing I'm not, you know, because I enjoy what I do, and it's really hard to get into orchestras. As we all do. So the answer I was really looking for, and don't worry about it, nobody ever gives me this answer, is that maybe there was something about the design within the length of the tubing that was robbing the energy on that partial. I was taking it a little further than you think maybe you should go, but that's all I do, really. I mean, the majority of what I do, or I used to do, is find ways to prevent the energy loss. So on a G on a Bach, if you play a Bach trumpet, you'll find that the G is more difficult, G and A is more difficult on most Bach strads than on Yamahas. And a lot of people play Yamahas because they're more consistent. And then there's the argument, well, but a Bach sounds like a Bach, and Yamaha doesn't sound as interesting or vibrant or colorful or whatever. So you have this huge dilemma. Bach people, Yamaha people, some of us play both, some of us won't play either. I've owned tons of all these horns, and I think they all have their strengths, you know, and their weaknesses. But there is something physically different about a Bach trumpet that really creates that problem in that F, G, A zone. And I'll just tell you what it is, because it's the first modification I started doing years ago when I would modify Bachs, is I would take that S brace off right here. You know, that S brace goes like this. And I would pull it off. And my theory was, actually it wasn't really much of a theory, because I'd pretty much proven it was true. Because I'd gone into the lab and I discovered with an ultrasound that I could see that the antinode in that zone of those partials was right here. And it was vibrating this tubing a lot. Well, I also knew that in order to bend this tube and create this curve, you had to take a straight tube, and then you had to fill it with something, sand or pitch or ice, and then you had to bend it around a form. And when you do that, then the outside of the form, or the outside of the tube, would then thin out, because literally the atoms or the molecules have to stretch out. Well, because they do, then you have thin tubing here, thicker here. The antinode just happened to land right here. And because it did, then the antinode was literally vibrating this section. There was so much high pressure energy inside here that it would overcome inertia and set this section into motion. And we would literally have a transfer from a sound wave into movement, okay, movement of the material, which is what I basically term as an energy leak. And the more you would give it, the more that would happen. It would just keep leaking energy there no matter how much you put in. Well, when I realized that, I thought, why don't we just brace that right there or make it thicker? So one of the first things I did was I bought some of that Sculpey clay, and I put it all over this area, and I baked my horn in the oven. And then the problem was gone. And I thought, wow, that's crazy. I actually fixed that problem. The only problem was my horn had a big chunk of clay on it. And Jen knows, I experimented with clay for many years. Different types of clay would have different effects. If you have an air-filled, really lightweight clay, it doesn't really do much sometimes. So I messed with that a lot. It always played better with the clay unbaked than baked, unless it was really hard clay. I learned all these things about clay no one should ever know, and I don't even use it anymore. But eventually what I did was I took that S brace off, and I reversed it, and I'd make it kind of wrap around there a little bit. And if any of you have seen the AGR videos, the adjustable gap receiver videos that I've just been putting out, then that's what I recommend you do when you retrofit an AGR on your horn, is take that brace off and then refit it at the same time. You might as well, because you have to take it off to put that on in the first place. And then that, a lot of times, will solve that issue. And that's one of the biggest problem areas. I played in orchestra and chamber orchestra all through school, and I constantly found myself playing G's and A's and having trouble again and again. And then when I fixed that problem, all of my friends were lining up to have me change the horns, and I had tools and a torch in my dorm room, and I would do modifications right there at school and work with players. And that eventually, over the years, led to me building horns, because eventually there were so many people asking for things, and I said, well, I should just do this, So then, year after year, I cut down my studio and my performing until eventually I just did this. And saved a lot of money until I could eventually build my own homes to do it the right way. But everywhere there is a tubing bend, then you're probably going to have this problem. The reason Yamaha didn't have as much of a problem with this as Bach, the problem is still there on Yamaha. A couple of reasons. But the way that they bent this was a little more sane. It wasn't as extreme, so it's not as thin on the outside. And then also the proportions are a little bit different on a Yamaha. So if you were to measure everything out, then that anti-node really ends up closer to the brace on a Yamaha. So then the problem can be solved that way too. Now Yamaha knows this stuff. Yamaha understands it. I know that because where I learned to study the acoustic side of instruments was from a scientist from Yamaha. When I was in college, we had a visiting professor who was a scientist. He was an acoustician at Yamaha, and he held some classes that were basically the acoustics of brass instruments. I was like, are you kidding? I had already been doing this stuff for years. I was like, I have to take that class. And then I was like glued to this guy the whole time he was on campus, learning how to measure the horns, learning how to use lab equipment, and really understanding the fundamentals, because what he did was he was basically in charge of the department of making Yamaha acoustic guitars sound as good as Martin acoustic guitars. And eventually they achieved that. I mean, really, Martin has its own name and its own line, but Yamaha guitars are just as good or better. And that's because they completely deconstructed the guitar and understood what kind of bracing scenarios worked right, worked best to resonate different frequencies and to project different patterns. And if you were to look at a Yamaha guitar today, like go into the showroom, try different ones, they have models that do specific things, just really kind of like what I do, just on a simpler level. But if you want a guitar that really projects, or if you want one that's good with pickups, or if you want one that has both, an acoustic pickup, whatever, then they've got you covered because they studied it all and they understand how to brace it and how to create it. So that's where I really started thinking about bracing, and also material, to really prevent these problems and to prevent energy loss in specific areas. I took that a little bit further, and eventually I made the entire lead pipe and tuning slide and the valve casings as efficient as I could without making the horn either too expensive to produce or too heavy to hold. Because there's, with anything that we do in life or anything that we design to build, you basically always are bound by natural laws. If you want to make something that's extremely efficient on the trumpet, but you want to make it very lightweight, then the cost goes up. If you want to keep the cost down, the weight goes up. If you want to keep the cost and the weight down, then you have a regular trumpet, I mean, and that's true, because you have to be able to balance all of these different laws of nature. If I were to make this trumpet play just as well as it does now, but half the weight, it would be made out of aluminum. How many of you want to play an aluminum horn? Why not? Did you know aluminum is more efficient than brass? It's weird, right? An aluminum trumpet would actually sound better than this. And nobody wants to believe that's true, except when you talk to aerospace engineers. Because an aerospace engineer will be like, well, of course aluminum would be better. Why don't you make them out of aluminum? I was wondering about that. You hear stuff like that. Well, I don't make them out of aluminum because traditionally people want to see them in brass, And why do we work with brass? Because when we started making brass instruments, aluminum was either not discovered or was so rare that people didn't know it existed. They didn't know what it was. Aluminum is not naturally occurring, so it occurs as like something else. It's usually a salt. And then you have to extract the aluminum out of it. So people didn't even know aluminum was available or existed. If they had known, they still couldn't have made trumpets out of aluminum, because aluminum is very malleable, so you can shape it into different things. But it heats up very quickly. It's a great conductor. And when you go to cut something, say on the lathe, because all the parts that are round are cut on lathes, if you were to cut something on the lathe out of aluminum, then the temperature gets so hot that with standard cutters, the aluminum will weld itself to the tip of the cutter. So then you couldn't use it. 100 years ago, 200 years ago, there are a lot of reasons we didn't use aluminum. But today, I don't know that there are many reasons not to use aluminum, because aside of durability, not like brass is really that durable anyhow, there aren't that many reasons to stay with brass and go to aluminum. The reason I don't do it is mainly because customers want brass. You know? I would put a lot of money into equipment just to cut aluminum if I could see the potential of everyone out there saying, oh, that's a good idea. Now, in 20 years, after people have really had time, absorbing what I've done here, then maybe aluminum will be the solution. But it takes time for that change to happen. And of course, today,
I have a question. So the problem that you discussed with the Bach on the end of the bell there.
sure.
You don't have any bracing at all there. Are you dealing with that with materials or with mass?
I'm not. The problem still exists on this one. The reason that you don't notice it, it's a great question, is because on a Bach, all right, we have what we call transmission theory, which basically states that anytime you transmit energy through a medium, then the energy loss is accumulative. So if I lost 10% of my energy here, then I'm at 90% there. If I lose 10% more, then I'm at 81%, so on and so forth, right? So, and I didn't know that stuff. That the people that taught me that were engineers that actually deal with radio waves in the military, because they build these huge antenna arrays and things that basically they were putting too much energy into the antenna that's 40 miles long to communicate with a nuclear submarine, and they had to find a way to make it more energy efficient, and they were losing energy cumulatively, so it just, as it went down the line, it was losing energy. The same thing happens on the trumpet. So on say a Bach trumpet, you do lose a lot of energy right here at the receiver, because the receiver is close to some of the antennas, and it starts to move, okay? And because it does, then you have energy leaking out. And then you have another antinode down here, and the energy leaks out, another one here, and the energy leaks out. And then you've lost, say, 50% of the energy, right? Well, nothing's 100% efficient, and acoustic instruments are no different. We lose a lot of energy in vibration, and that's not going to stop. But, we don't care because we make good music with them. But we do want to fix that G and A zone. So what I did was, I made the horn very efficient on the first half of the tubing, actually even more than that. And then when it finally gets to the areas that were always a problem, so much energy has been preserved that it doesn't even matter if you lose it. Actually, the weird thing that happened with that was now this does move. It might even move more. All of this might move more except for that bracing in the middle. But the cool thing is, so much energy is getting there in the first place that now we hear more of the movement. And that goes back to your answer, which is you were saying that the waves could be a little bit out of sync, or there could be some kind of other type of wave in there that interferes with the original wave. That happens on trumpets. It happens on all instruments. If I create a graph with equations in using math and say this is what the spectrum analysis of this taper should be. This is what the sound spectrum is going to look like. And then I put it on a spectrum analyzer and I say, all right, let's compare that and see. The spectrum analyzer picks up stuff that I couldn't even predict at all. It's like, what is this big mess? I mean, there's a mess down here in the lower overtones and in the middle, and the upper is just, I can't even tell where anything is, And for any of you who've looked at spectrum and spectrum analyzer readings on overtones, basically what they do is they show the amplitudes of all the different pitches, okay? So when you play a low C, you're actually hearing a high C. And whether you hear it or not, it's there. So if I play this, I'm actually hearing this. All those overtones are in that C. And that's true of every note. You hear the full overtone series. So the spectrum analyzer can pick that up and say, oh yeah, we hear a little of this, a little of that. Sometimes what happens though is our ears will hear a low C, but there's almost no amplitude to the low C. So the spectrum analyzer says there's a pedal C, there's the G in between, there's another C, but there's no low C, or it's hardly even there. When that happens, it means that there's something wrong with the instrument. And your brain is filling in all the parts and says, well, all the other overtones are there, it must be that note. So your brain tells you there's a low C even when there's not. Not to get off on another subject, but that's what Bose does. The speakers, they create the illusion that there's really big sound when sometimes they don't even have the capability within the mechanism to produce them. Sometimes they wrap up a bunch of tubes in a box and they can create low frequencies. But they'll intentionally create the impression from studying sounds and the way humans like interact with them. And they'll create what is most of the sound without the lower overtones, and you'll think that you're hearing grumbling sounds when they're actually not, which is pretty weird. So, I forgot what the last question was I was answering. I got off on too many tangents. But
I've got an additional tangent
sure.
question.
All right, I'll come back to your interference thing in a second. Go ahead.
Oh yeah, the interference thing. I was just wondering, like, you pointed out the problem with the Bach and the way you went about solving that. Are there other kind of like common problems that you see in maybe like a factory-produced trumpet or whatever?
There are,
And
yeah.
Could you give just an example of one maybe?
Sure. The mouthpiece cap is probably the biggest one that I see again and again. Because in a factory setting, someone draws a lot of tubes and lead pipes, okay? And for Bach, you have usually 25 lead pipe, a 4 to 3 lead pipe. Those are the two most common. They have other slight versions of them, like there's an older version of this one. The difference between a 25 and a 25-0 is that someone who trimmed the end of the lead pipe, well, let me explain this. When you draw a tube over a mandrel, basically that means that you took a piece of tubing and then you attached something to one end to be able to pull it really, really hard to exert a lot of pressure to stretch it over top of a mandrel. It's like tapered. So when you do that, the other end that gets pulled all the way to the end of the mandrel has a little like nib on it that's the original small diameter, and you have to cut that little nib piece off. So you take it over to a bandsaw and you slice it off. When you slice it off, then you have to shave the end on a grinder or a sander of some sort, and then you have it squared. Hopefully you deburr it if you're doing a good job, and then you hopefully would measure it. Well, the way you would measure this would be to use a set of gauge pins. The gauge pin is at a certain temperature and humidity. It supposedly is accurate within whatever is stated in the set. But my set is like 1/10,000th of an inch or something. It's really accurate. So you take the gauge pin, you stick it in there, and you find that the 3-4-5 gauge pin fits in perfect at the end of the lead pipe. Then you take 3-4-6 and it doesn't fit in. Well, now you know that the size of the venturi is somewhere between 3-4-5 and 3-4-6. You know, somewhere in that range, which is close enough. I mean, we're down to thousandths of an inch. You know, if it were medical stuff, we'd go further with that. All right, it's just a trumpet. So what happens at like a Bach factory is someone trims them all, someone squares them up. They come in bins. They're all done with them, right? And it could be a lot of different factories. But when they're all done, someone goes to measure them. Usually they don't have a full set of gauge pins. They have one pin. Is it bigger than this one or smaller? Well, it's smaller. Make that a 25. Oh, it's bigger? 25-0. Okay. So now you have a venturi issue because you don't actually know which venturi they are. They don't know. So you go play test a bunch of horns and you're like, man, that one plays great. This one's all right. This one feels good in the upper register, but there are other problems. So now you have the venturi problem, right? The second problem, which I was getting to, is gap, which is related. Now, when you stretch that tube over top of the mandrel, then the outside of it also became tapered, okay? Because the wall thickness just stretched out. But depending on how far you stretched it, the wall thickness could be greater or smaller in thickness, right? So let's just say that the thickness is 0.02 inches or 20 thousandths, right? But the guy who's working on it that day, you know, he had a late night and he's pulling them out, but he's not working as hard. It's usually like a crank machine, okay? But today it's probably unended. I haven't seen one in a factory in a while. So now they're pulling them off and they're like 0.021 or 21 thousandths. Well, you think, what's the difference? It's within a thousandth. Except on a taper, a thousandth is a huge difference. If I were to cut the shank of a mouthpiece like this and put it into a receiver like this, what holds them together? They're stuck. Why do they get stuck? Why are they held together?
Taper's the same for both sides.
Taper's the same, so then you have so much surface friction. Because if you were to measure that surface area, it was like a square inch. There's so much there that they can be stuck together. If you twist it a little bit, then literally the molecules are almost getting stuck together because they're all meeting, you know? It's like, have you ever taken a perfectly smooth surface? Like I have granite plates in the shop, which are ground to an absolute, as close smooth as it can be. And if you lay something on there, like one of our inlays, we have inlays in our finger buttons. Well, we use a lapidary machine to make these perfectly smooth, and it's a diamond honing machine. When you lay the inlays down on the granite block, they get stuck to it sometimes, almost like they were glued to it. And the only way you can get them off is to slide them off. You can't pull them straight off because they literally like create a little vacuum. You can't get them off. So something similar happens here. The mating surfaces are so hopefully smooth and close together, and then if you give it extra force, it really sticks, right? Okay, well the same thing happens when you stretch a lead pipe and you create the little taper. The lead pipe has a taper too. And then that goes into the other end of the receiver, which my receiver is a little different. But if you look at a regular trumpet, I don't know if that happens. Okay. Yeah, so what happens here, so now you can see that that lead pipe is a taper, okay? This tube was smaller than the very end, and it got stretched over the mandrel, pulled it off, and then they trimmed it. They found out if it's a large one or a small one, and then they stuck it in the receiver. Luckily, the machine that makes the receiver is a computerized machine that probably holds pretty close tolerances. So if the operator is doing his job, then they're accurate. Let's just assume they are, okay? When you put that tapered section in there, because it's a taper, and because the mating taper is the reverse of it, it'll stop at some point, just like a mouthpiece does in its receiver, right? Same thing. The only problem is, if the guy who stretched the tubing that day stretched it just an inch longer or an inch shorter, then the wall thickness was a different thickness, okay? Because it was, then this lead pipe either went in further or less on that one than the next one, right? So there's an inconsistency. The only way you could determine that variable or control it is to have some mechanism in place in production to say, hey, you can only go in this far, or these are rejects. But there's nothing like that in place. I know for sure there isn't, because I've measured hundreds of them and they're all different. So, if it goes in a little further, one goes in further than the other, when you put your mouthpiece in the other end, then your mouthpiece, of course, seats in there, but on the inside, imagine the lead pipe actually is a tube that's coming this way. So inside here, there's a space between the two, the gap. And I'm sure most of you know about gap by now, because everybody's talking about it lately. But the gap is the distance from the end of the shank of the mouthpiece to the beginning of the lead pipe. And the reason it varies is because people produce different tapers of receivers. They draw lead pipes slightly different, like you just heard. And of course, the shanks and mouthpieces are all different. But even if all that stuff were consistent, you could still have a problem if that guy, just who was drawing lead pipes that day, made them a different thickness. The reason this is such a big deal, and I talk about it so much, is because it's one of the biggest variables in the trumpet. How else can you explain it? You go pick up 20 different Bach trumpets, and then you find that one or two are the best ones and the others aren't. It's a good thing that they're all slightly different, because then we can try different mouthpieces and hopefully find a fit between all of them that gives you a gap that feels good, regardless if you know that stuff is happening or not. It doesn't matter if you know about these variables or not. If Phil Smith says that his Bach plays amazing, I believe him because he sounds amazing. If he sends it off and has it refurbished and brings and plays it again and says, man, it doesn't play well anymore, then I start to question what's going on, because you have to think about that. How could just taking some dents out and replating the horn have that big of an effect? Except that when you plate the inside of a receiver, your mouthpiece doesn't go in as far. So now there is a change, and that's not the only change, there are others. So yeah, to answer your question, the production of the lead pipes and the way that they fit into the receivers can be a very serious inconsistency. It's not really related to energy loss, it's more related to an impedance change, close to your lips, and airflow. But yeah, the venturi sizes vary between horns. Yamaha is probably the most accurate. They have variables too. We all do. The only difference is I just tell everybody what the variables are. On mine, you can just interchange the insert itself, which is essentially the beginning of the movement. And the insert itself, which looks like this, they're all precision machined, and then of course I actually hand check every single one with gauge pins and find out which size they are. And the nice thing is my machine is accurate enough that if I need to make 20 of these in a row, then it really does make 20 in a row, and not even different. But I still test them all. I check them all. But that way, you can determine yourself which venturi size and which gap solution is going to work for you, because that is a variable we should really, account for. And it's probably the biggest variable besides efficiency. Mouthpiece gap and the venturi size are probably the two most personal things after your mouthpiece. Some people play trumpets that were made in China or India or made 70 or 80 years ago, and they're falling apart, and those people sound amazing on them sometimes. And there's got to be something about that instrument that works.
Motion sensor.
Oh, it's just motion.
Yes, it is.
That was a quick motion sensor. I'll keep moving around. So, is that it right there?
Yeah.
Okay, so, yeah, so, all of those little inconsistencies in production can add up to a lot, especially because we use tapered parts. It's because these parts are tapered and there's not another system that's a cylinder that locks in place, that this is a problem in the first place. Modern machine design today, we don't use tapered mating parts that are precision ever, because it's so difficult to make them consistent. So, I would say in the next 10 or 20 years, hopefully the higher end manufacturers will get away from tapered altogether. I mean, I will be. So, hopefully it'll be a trend.
What do you think? Something threaded or something? Just push it in,
with this
turn
system, something threaded makes a lot of sense,
Yeah.
because we can interchange the end of the lead pipe. But I've experimented with a lot of different systems that would work. A collet lock system would work really well. If you've ever seen, here's a flugelhorn right here. Here's a flugelhorn. We've all seen this little device, which is not really the best invention. But this is just a simple clamp that squeezes the tubing down. And it distributes force in a really uneven way. It's not very good design, but still we get them on flugelhorns all the time. And this looks like a Harrelson. So a system like that, I would not recommend, but it would probably be better than this. But it would be very simple to create a collet lock system where you just have a little screw down, and inside there is a collet. And a collet, most of you probably don't know what that is, but it's basically a sleeve that holds a tube, and the sleeve itself is expandable. It can expand and contract, and when you tighten a nut over top of it, it has a tapered wedge system that just clamps down on the part. So a collet lock system would probably be the very best system. It's a little more complicated, but yeah, I would see that this has to go at some point, because the reason that I created the 5mm, the modular mouthpiece, which is what this is so that I could correct a lot of those problems, or so you could, because then you can find the length of the taper and the type of taper that's going to work with your horn the best, or you can put an adjustable gap receiver on it. But all these things are designed to just solve a problem that was invented 150 years ago when they decided to use a Moore's 1 tapered shank, and it was a simple solution back then, but we should have abandoned it.
They change over time too, as they wear.
Yeah, they do. If you have two of the same mouthpiece, they could be different. It depends on how they were plated or how they were machined. Machining a taper is relatively difficult, even on CNC equipment. There's a basic rule I was talking to somebody about earlier that says you should never machine on a lathe a hole that's more than 3 times the diameter of the part. Or in other words, the diameter of this part at its smallest is very small. This is like 0.4 inches, okay? But then the length of it is 3 So that's like 3 or 4 times the rule. You're not supposed to do that. So the way that mouthpieces are made, technically, almost all mouthpieces are made against what would be considered best practices by machine shops and by the whole industry. Because there's too much run out. When you spin this, it's spinning too far. When you have a small tool that has to go all the way down inside there, it deflects too much. So there's no possible way for you to have any real measurable accuracy from one to the next. Even small chips that get between the cutter and the part can create gouges in there, and they do. I've cut tons of mouthpieces apart. And inside them, when you look as a crosscut, you'll see that chips have created gouges all through the back bore and the throat of the mouthpiece. Well then, then even there's no consistency in the mouthpiece. So that's another reason the 5mm is broken into small pieces. So you can see this is the back bore, and I'm still breaking the rule, but not by much. By making this part so short, then I can ensure that it's much more accurate than normal. And all the parts are broken into smaller pieces, so that one, we have accuracy, and 2, you can interchange all the parts. So if you want, this over here.
Actually, I'm going to put it outside.
Awesome.
Wow. It's really bad. Crazy.
Is there a light switch?
I don't know where the
What's right
motion
next to you?
There might be a light switch over here. Oh, there we go.
There you go.
That's all Trump.
All right. So if you wanted a, let's say you really like a shilty rim, but you want a shilty rim on a box mouthpiece or something like that, you could just interchange all the parts. Makes life a lot easier. And it simplifies the process of finding the setup for you, especially because rims are such an important part of, the interaction with your lips. So, all right, to get quickly back to the question about interference. This always happens when I start talking, I just never stop. So we're talking about how there's interference in the standing wave that can sometimes prevent you from hitting the pitch. And I know I'm not quite on the exact question where I was, but I don't remember where it was. So if anybody remembers. What happens here is because this whole section loses a lot of energy, it will vibrate. Literally, the antinodes will cause the bell to vibrate. And if this were a lightweight bell, which I do make, then it would vibrate even more. But because I conserve so much energy up front, then I can lose some. You will hear more behind the bell, and you'll hear a lot more in front of the bell. So then everything sounds and feels better. If I were to make all of this really efficient, which I've done, then you don't hear anything behind the bell, just a little bit. And then out there, everyone hears so much that it's overpowering. So it's difficult to have a good balance between the player and the audience, which is why I do not put bracing up here on a lot of my horns. It's because I just focused on saving energy in the front end and losing a little more on the back end. But you don't lose enough to really notice it. We notice the efficiency gain, even though there's even more energy loss in these phones. But interference happens because when on certain partials, especially in the very upper register, like high C and above, then what happens is sometimes you will get a wave. It's not really a standing wave, but it's a different type of wave that will bounce back and forth between the last brace and the bell rim. And that little wave creates other stuff that possibly could explain why the spectrum analysis doesn't match up with the theory. Although there's controversy over that, nobody really knows for sure if it's true, or if they do, they just probably aren't in my field.
Is that a mode in the metal, or is that a mode in the air column?
It's in the metal usually, yeah. I mean, it's not really a standing wave, so it's literally like, because this is moving, then you get other types of waves that bounce back and forth in the material. And it doesn't just happen there, it happens everywhere. But mostly on my horns, here to there, and here to there.
Yeah, it was an interesting demonstration that I used to have in a physics class I had where they would take plates, and you take a bow from like a gel or something, put sand on the plate, and run the bow along the plate, and the sand will kind of organize itself into patterns.
Right.
And those are, modes of the metal.
Exactly, because the metal itself is resonating, and wherever the sand is congregating is the antinodes. So, and then of course, ultrasound technology allows you to see that without any hand. Because you could look at a trumpet or even a plate or the head of a drum, and you can see that because the ultrasound can actually, like, if you put it out of phase, it can, you can create a video screen effect of it, basically it creates a representation of what's happening. Exactly. So the metal itself is, and on a trumpet bell, it's really interesting because if you have an antinode right here, right? Let's say the antinode's right here. Then you will get like 6 or 8 nodes, and they're little ovals that go around the bell. And that's just what you're describing.
Yeah.
It's the same exact thing. So then within that, there are parts that are moving more than others. There's little ovals in there that are not moving, and then areas around them that are. And it creates these other waves that create interference, and you notice it most in the upper overtones. And you hear that most on Schilke trumpets and Colicchios. Schilke, he truly believed that you should be able to hear and feel the sound from the player's standpoint. I mean, he was principal player. He was, one of the most sought after players of his day. And he believed that when you test the horn, you should really be able to feel it and hear it all around here. But he didn't really do enough testing to see if it was getting to the back of the hall. I was talking about this last night, but if anybody's played the new Tiger trumpet or the P-bone or any of those plastic horns, then they too will convince the player into thinking, wow, this horn plays pretty good. Except the people across the room won't even know that you're playing because the sound wave doesn't have enough energy to carry over there. It gets lost in all the stuff. And that's because so much of the energy on an inefficient instrument is being bled out in vibration. It still sounds like trumpet, but it's coming out this way instead of that way. Because that's just what sound does. A sound will dissipate in any direction, wherever it can be lost. So when you play a Tiger trumpet, if you wail on it in here, then on the other side of the room, other people could still have a conversation. Whereas if it were a brass trumpet or an aluminum trumpet, they'd be like, "What's your problem? Why are you blowing your horn at me?" And that interference can really mess up. On a plastic trumpet, you won't even notice the interference because there's too much energy loss. But on a good trumpet, you
So
won't.
those aren't really correlated with the air column at all, right? So they're
No.
not going to support any of the frequencies you're trying to get. They're not going to support any harmonics.
But what happens, they do sometimes. Yeah, they do. Because on a Schilke trumpet, like people talk about the brilliant bell, what happens is the tuning bells on Schilkes were really popular in the 70s and 80s, and sometimes today too, like John Faddis, for lead charts and commercial music, right? Well, these guys really get into playing these horns because they can hear it, the section can hear it, and the microphone can hear it. Because these guys play in the mics, or they do recording studio stuff, right? Perfect. But you would never see a Schilke tuning bell trumpet in an orchestra playing Mahler. Why not?
You gotta play the back of the hall.
Exactly, because everyone's going to say you're too bright and you're too loud right here, and the conductor's going to say, when are you going to play your part, right? And we all know what that's like, well, a lot of us do, where you feel like, hey, I'm really projecting and I'm creating this big, beautiful sound, but the people out there are saying, yeah, it's not all right. And you're like, what? I put everything into that. Well, it's because you're not hearing what they're hearing, and you never will. On my horns, on a Monette, on any horn out there, you're never going to hear the same thing behind the bell as you are out there. And last night we were playing that gig, and you were in the section. And what did you hear when I played?
Not much,
Yeah.
really.
You didn't hear much. I was in front of the band, and you're back in the section, I don't know, like
Back, I was,
20 feet behind me,
yeah, probably about that.
and off to the side. Yeah, but then everyone in the audience was like, oh man, that's a big giant sound. I should have turned this way a couple times so you could hear it, But then today he came in and I was playing, he was like, oh yeah, it sounds completely different.
It does, yeah, it's way bigger.
It's because the horn is going to project out there, because that's how I designed it, was to project out to the audience. You actually will get a fair amount behind it. But if I were playing a Schilke, you would have said, man, that sounds great. And the audience would be like, when are you going to play? And that's the give and take of projection patterns and efficiency. So tying that all together, what happens on a Schilke trumpet, like a Brilliant bell, when you're playing high C to G, and you're doing like the fun fifth thing at the end of a piece, right? And you get this sizzling, bright, beautiful sound. You know, like, oh man, that's the perfect lead sound. I love it. Well, what's happening there? You're setting up an extra set of vibrations, physical vibrations in the material, between here and there, that then reinforce some of the very upper overtones of the note that you're playing. So it just so happens that because this is short, and then it would literally vibrate at a higher frequency naturally, then it reinforces the upper overtones in a thin or bright or inefficient setup. So that's why Schilke and colliquio horns, or a lightweight bell, will sound not just brighter, but almost sometimes like so edgy, or people have different words for it, but like they cut like a knife or something like that. It's because usually they, depending on what note you're on, that vibration between the material is almost always going to be the same frequency, because it's fixed between here and there. But the note that you play is a different frequency. So if you measure this on a spectrum analyzer, you will see that that one is always there. That whatever that frequency is that I attribute to this is always there. If I play a high G above C, it's there. If I play a G sharp, it's there. If I play an A, it's there. Now, what was that pitch? If that was a G sharp, then my G sharps sound nice and clear, and then the G's sound like cutting edge, and it's because they're a half step apart. Except I'm kind of exaggerating. They're never a half step apart. They're like an eighth of a step apart, and then they sound like really edgy because they're out of tune. But they're so high up, and we don't listen to that stuff enough, or we're not fine-tuned to it. We don't know what to call it. We just say, man, that horn really cuts. That's why it cuts, is because it loses energy, and the frequencies just get to be such a mess up there that it's shrill. It hurts.
I guess that would be affected by the location of the brace there too, because the Schilke's all have the reverse pipe on them. So the brace is kind of, if you don't have the tuning bell, the brace is closer to you than.
And if you have the tuning bell, then you move it in and out, and it changes too.
Yeah.
And if people have created braces that are temporary that can go in there. I used to test with my own homemade braces all over the horn to test for things like that. And unfortunately, it took me way too long to figure out that what I probably want to do is keep the efficiency on the front end of the horn. I was focused for like 10 years on bracing the bell different ways to find the perfect bracing scenario to create the best sound on every note. And then one day I found out you just can't do that. So you can't do everything you hope to. So that's the horn side. I'll answer questions about that, and then anyone that wants to continue, I'll talk about embouchure and